Okay, what sort of information requirements do we have? Well, we need to know all the physical parameters of the situation, need to know how they relate, what our status is, as much about the other person as we can determine. The information requirements analysis, we're kind of laid out here in template format using the IDEF notation. What we're going to do is use the results of our task characteristics and our critical factors as some sort of control mechanism on the task that we've defined. Take a look at the underlying process and mechanism models. We'll spend a little more time with them in the next module of the tutorial to generate our information requirements list. That and the processing models then flow into the system concept definition, where we analyze the validity and the utility of the results that we've generated. The information processing mechanisms themselves can be thought of as taking a look at how we actually handle information within the environment that we work with. In this chart, we have a nice dividing line between, on the one side, all of the silicon-based computing intelligence in the system and all of the carbon-based computing intelligence in the system there. We realize that we need to be able to put that together and to determine what the mechanism is to generate the output required to stably control the system and achieve maximum mission success. We do that by recognizing that the strategies that we're going to take a look at from a conceptual design viewpoint can be best expressed in terms of the ones that are familiar to us every day as human beings, realizing that they do have computer components and counterparts also. So we have three major categories that we're going to take a look at here, and we've got a set of definitions of each one of the major classification elements that we can refer back to within what we're doing. The major ones to focus on here are within the knowledge structure itself, to realize that we have a fundamental difference between doing mere fact recall and data retrieval and the application of concepts and principles, which is fundamentally a very high order processing mechanism. The decision processing mechanisms we've already covered in terms of the complexity and the way we type them, and so we're able to discriminate between the processing required for them. The information management itself runs through the entire gamut of being able to acquire, manage, control, correlate, project into the future, make some inferences on what's likely to happen, and determine what sort of assessment is necessary to complete the picture. What we've done with this slide here is to take a look at our mission-oriented task and just go through in a very common sense approach, guided by some of our subject matter experts, to determine where major chunks of knowledge processing, decision processing, and information management occur. This first cut gets moderated several times and is reviewed at many different levels to complete the picture. The completed picture that we're going to work with, having been through a couple of iterations, is best expressed by this view graph, where we have the three major tasks that were recognized within the mission decomposition that Kevin produced as having multiple interrelated tasks in a compressed time environment, and all of them having high criticality to mission success. And those are the maneuver to intercept targets, determine the weapon firing sequence, and maneuver to launch position. And in fact, this problem set that we are working based upon the video that we saw is the very first part of this maneuver to intercept target, which is determine the optimum tactical maneuver. We're going to further decompose that as we get into the model that we're going to use to assess the value and the worth of the conceptual design that we're proposing. Now we try to gather as much information together as we can, put it into a format that's readable and usable by a wide number of people for a lot of different purposes within the data gathering, data processing, and report generation format. So we put together several different sorts of worksheets here, and you've probably seen some of them. They're aids to collecting data and to presenting it. Hopefully it helps to focus the critical evaluation that the many team members on our Tiger team are able to bring to resolving the problem. Okay, within this one here, over on this side, within this one we have the tactical objective is to maneuver to intercept target. Our task is to determine the optimum tactical maneuver. We fill in the first part of that based upon what we've already done. We've captured off what the information processing mechanisms are. In this case, there's no knowledge structure to speak of that needs to be handled. We have a recognized Type 2 decision processing mechanism, and we have no very heavy information processing, information management mechanisms there. We're able to write up the characteristic statement here that presents it in a nutshell for anybody, and then determine what sort of information requirements we've got. We realize that we need to be able to assess the intercept geometry. That's primary. We need to be aware of the EW situation in regards to both our own capability and the other target. We need to also have an idea of what the target raid is like. Is it only a one-on-one encounter, or are there more hidden within there? Lastly, we need to be able to analyze that several different ways and be able to provide an assessment of what these results are. As we tier down within the subtask structure, we find this one is analyze the intercept geometry, perhaps the most important component of what we had over there. We recognize that this actually does have the necessity to do some fact recall and to apply some concepts within it. We're going to take a look at what they are in the next module. There's not a lot of decision processing involved, but we do have the requirement to acquire and to correlate some of the information that we managed to obtain. We write out the characteristic statement and realize that we have the information requirements from that. And these information requirements are basically to correlate the target aspect angle with the optimum target aspect angle to guarantee the highest level of probability for mission success. We need to correlate what is referred to in fighter weapons school as antenna train angle. That sounds like we've committed to a technology, doesn't it? Antenna train angle. That would be radar. Well, in fact, that's really just the statement within the training curriculum that's the difference between what your velocity vector is and what your instantaneous line of sight to the target is. It does have a radar component to it, but we're trying to keep this separate from the technology that could be brought to bear. Lastly, we do need to know what the range of the aircraft are during the situation itself. This is, of course, one of the fundamental physical parameters and is used to gauge any number of things within it. We tried to keep the number of information points to a minimum so that we can express it simply in a model, analyze it simply in a model, and build the added complexity after we've decided that it's really worth doing. So here we've listed out for our 3 mission objectives and the most important of the task, the information requirements themselves. And this entire thing flows throughout the package. We realize that, in fact, there are some other things that need to be brought to bear when you concentrate on different aspects of implementing the mission plan itself. And these things feed back and forth. It becomes a very complex, dense situation. We're going to focus on the one thing, analyzing the intercept geometry for its contribution to situation understanding, because this seems to be the crucial part, the heart of the problem that we've come to within our video this morning. So we understand that within the knowledge structure itself, we've got a concept application to be made. Over in information management, we have to both acquire and correlate that information. This just lays out the fact that we recognize what our processing components are. We've got some idea of the strategies that we have there, and we realize that what we need to do is to develop some sort of logic to determine optimum intercept geometry, to be able to assess that. This is probably the key point of what we need to do both tactically and within our design criteria itself. If we can't assess the validity of that optimum intercept geometry in a simple model, it would likely prove difficult to mechanize in any sort of realistic fashion in a tactical environment. Okay, we're having finished up the information processing. Are there any questions about what we're really trying to do to resolve the problem that we've been handed as a Tiger team? Okay, we're going to jump into the concept definition of the system. Remember, this is, in Fred Brooks's words, trying to take a look at conceptual design issues that allow us to define the system and make some design issues known early enough in the game that we can in fact do something about them. This gives a real quick overview of some of the distinctions between the concepts and the functions. We have a couple of aircraft concepts up there, and it's fairly easy to take a look and notice the distinguishing features, some of which are noted, some of which aren't. For instance, the biplane, an older design, does have retractable landing gear, whereas the monoplane, a newer design, doesn't. In fact, to be able to evaluate which concept is best, we need to understand what the domain is that we're working in there. In this case, our domain is pylon racing. So we have a mixture of both straight line performance and turning performance that needs to be blended together to achieve a winning racer within the pylon. Knowing what that function really is, we're then able to apply all the aerospace and physics formulas to determine what the relative advantage of the monoplane with cleaner drag and higher speed on the straightaways is relative to the biplane with a better turning radius, more lift, however higher drag on the straightaways. Without bothering to actually make the decision here, because we're not going to go pylon racing today, we move on and take a look at how we're going to analyze the concepts for the optimum intercept geometry. We recognize that we have at least one concept definition there. We're only going to choose one to grind through the crank today. In fact, we might have several different concepts, one behind another, that we need to evaluate in the real world. We decompose them into functions, run through a process model to understand what needs to occur within that, just like in the manufacturing realm. We have a system process description, and we have a set of algorithms that we're going to evaluate within that. Now, the algorithm that we're going to use to do our system concept definition analysis is listed out here. The functional component that we're taking a look at is the intercept geometry, maneuver to target, the components required to generate an optimum intercept geometry logic and to enable us to verify how good that is. We need to identify what kind of processing is involved, what the information needs are. We need to be able to structure this candidate algorithm, and we'll spend a little bit of time taking a look at that in a simple physical model later. And then we need to determine both, can we specify the processing model in sufficient detail, and is it feasible enough, and does it have the desired utility to actually make the prototype and the system work as we require. Okay, we have a system concept for the entire cockpit, aircraft, man, machine, and weapon system within modern fighter combat systems. We're going to focus on the situation assessment processor here. We're going to narrow down into the maneuver to intercept target, into the subtask, determine the optimum intercept geometry. We define a couple of things. Let's see, we need to actually put that one up. We also need to understand what the process analysis is like before we get into it. And recall, we've got here some sort of start and ending conditions there. We know from our previous analysis, in fact, we were going to need to do some information acquisition and correlation, and we're going to need to do some sort of concept application within here. We're going to then need to combine them and so that we get a viable output at the end. Okay, and move on to the next one. Okay, our tactical geometry assessment module then seems to consist of roughly two parts. And one of them is the description of what the volume of interest is and what the maneuvering space is. We have some physical keys here that we can realize in terms of everyday occurrence, and we'll put a diagram up in a minute. Basically, the volume of interest then is given the aspect angle, the antenna train angle, determining upon whether the target is a high altitude or a co-altitude or pop-up in this region here. We have a good geometric description of it. What we want to do then is to combine the output from our sensors, the target aspect angle, without regarding what sort of sensor it comes from, and the antenna train angle, again, technology independent, into our tactical geometry assessor. Whatever the processing looks like there, and whether it's a man or a machine, is not relevant at this point. We go on ahead and use the output from that to actually select the optimum maneuver, execute it, and then achieve the maximum level of mission success. And the last bit of information that we need to know in a qualitative sense rather than quantitative is what does our situation space look like in regards to a description of the engagement that we're about to commence. We happen to choose for this particular one the fact that both aircraft are in beyond visual range mode and that they both have an aspect. Now we go to a good geometric description of what the model looks like. We have the two aircraft here, the own ship, the attacker. We're able to determine what these angles are fairly well. No question about what the range is. And of course that's subject to change with the process of the engagement. We put together an algorithm then based upon the underlying physics and mathematics of the situation, because what we need to do is to maximize the volume that we can swing through in order to achieve the tactical advantage on the target. We want to come up with something that's going to both provide us a means of getting that and a means of telling us that in fact we have got some sort of advantage and that it's a sufficiently high advantage that we choose to continue prosecuting the mission. Maybe there are other decisions here than we've actually listed out, right? Okay, so we have a geometric advantage here that we want to compute. We realize that we need to express that in terms of the geometry of the situation itself. We run through here and come up with a formula that looks fairly simple to understand, fairly simple to implement, and we're going to put it into a figure that you can take a look at with a couple of examples and then give a tabular result. Okay, the figure that we've got is at the top here, and what this has got is 8 cases of varying target aspect angle and antenna train angle. Some of the cases that are the most interesting to us would be, for instance, case 1 down here, which has a crossing angle component of roughly 15 degrees and a target aspect angle and an antenna train angle of 15 degrees. We compute the tactical and geometric advantage of that as being a fairly high number. At the other end of the spectrum, we have down here bullet number 7, which has a fairly low tactical advantage to it. Why? Because we have a poor antenna train angle and target aspect angle for the situation itself. Having realized that in fact we can run through, automate a model that gives us some sort of good numeric values, we're then able to decide whether we have a sufficient tactical and geometric advantage given the position we're in. There are some ramifications to this. Obviously, if we have a sufficiently poor one, we might decide that we need to make some other decision processing choices within the loop. For the purpose of the analysis that we're doing, we're going to consider that we're able to achieve some sort of significant target geometric advantage and continue to press on and prosecute the attack. The worksheet that we've come up with to fill this in then looks something like this, where we have all of our previous information up there. We've realized what our what our mission essential information is, the sorts of processing and representation categories we have. The model that we have is multi-attribute utility. We've taken a couple of different physical parameters, analyzed them in a couple of different ways, and come up with a utility value out of them, our target geometric advantage. What the design spec algorithm is then, in a very general concept sense, is to evaluate the physics of the two most important quantities, determine the range to target, evaluate the potential for intercept according to an algorithm that we've got here. In actual practice, we might add additional terms to it, throw in maneuver capabilities. These are details of the implementation that we're not going to get into today. Okay, to complete the processing, we realize that in a general sense, this is outside of the specific detail that we've got for this one, that we need to have some sort of blackboard approach that enables us a global view of the most important models. We've listed them out here, and these are the ones that we found to be useful in analyzing most of the concepts within the outer air battle arena. And in fact, the one that we've chosen for this one is the multi-attribute utility model. We could have considered using things like fast time simulation or dynamic programming models. This would be differential games where you get into games of degree, kind, and capture, attempting to determine what the value of your intercept possibilities were. In fact, that might be another approach to be taken if we had had additional candidates to be evaluated through this process. Again, we chose just one to keep things moving through here today. Lastly, to wrap this up, we started out with a system prototype, had some sort of model selection of how we were going to run through things, defined our algorithm, chose all the information that was necessary out of these sorts of things, using as wide a range of concept as we could to generate that information, to represent it, and to display it. And now that we have completed the concept definition based upon the operational requirements database that I had neglected to show you that we'd finished earlier and submitted to the customer, this was the completion of the information requirements processing. We're going to take a look at the allocation of function based upon these models and then review the operator interface. Kevin, if you can get ready, are there any questions before we go to the function allocation?